So, part two. This is where it gets a little more interesting because you don't know if they're all acids. In part one, they were all acids. So, looking at A, you can see the back and forth arrows has turned into a box, but that is a back and forth arrow. This one is an acid, so just straightforward like the last, like number one. B is a base. It grabs a hydrogen, and the way to know that is this NH2. That's kind of a common base with the CH3, or you can have pretty much anything sitting over here, as long as it gives a lone pair to the nitrogen, as shown in the class notes on the Lewis structure, which I'm not going to attempt to draw on the computer. The KB will be in a table. The X is small approximation does not work here because X is not that small. You can do the ratio of KB to the initial concentration. Let me erase all this. So KB is 4.4 times 10 to the power of negative 4. And the initial is 0.02. And if you do that fraction divided by, then that gives around 50 without plugging it into the calculator. But anyway, it's not greater than 100. So the X's small approximation gives pretty close results if you look around here at what Dr. Spencer got. Moving on to part C. This one is just a base that splits off, strong base, very straightforward. D is same as before. E, I'm looking for one that has a conjugate base, and it doesn't seem, okay, now we have some diprotic. I'll go over that. So the diprotic acid, that means it has two hydrogens. We don't care about the second one hopping off because it's not going to be significant. So we have H. So here's our reaction. We don't care about it losing that second hydrogen. If you look it up in a table, it will actually list more than one Ka because it's can lose more than one hydrogen. So let's look up one of those tables. So you look up the table and you find this acid, and it has a Ka1 and a Ka2. That means the Ka1 is for losing the first hydrogen. The Ka2 is for losing the second hydrogen. So it is important to know that if you, I'll make a note here, if you were given HCO3 minus back and forth to that, oh no H. If you had this, then you would use Ka2 because it's the second hydrogen that is lost. And with this, you use Ka1 because it's the first hydrogen that is lost. So I'm going to erase the other example. And we use Ka1. I'll go ahead and write out the ice table formally. Initial is whatever it is, 0.05, and 0 of the others, change plus x minus x minus x, etc. You do the usual Ka equals fraction x squared over 0.050 minus plus x. Oh my goodness, I keep doing this backwards. I'm just trying to go too fast. But anyway, the important part is, for Ka, you use Ka1, which is on this table. So, Ka1, there it is. Let's put it in. Times 10 to the negative 7. And you do the math, and the rest is the same. I'm not going to show it. F, same thing. Ka1, first hydrogen loss. Okay, done. And now we have number 3. Estimate the pH of each solution below. Categorize these aqueous solutions below as appropriate.